a storm arrives tomorrow, it could be devastating.
The coastline at Seaford is more exposed to large waves driven by the prevailing southwesterly winds than any other frontage along the Sussex coast. Up to approximately 100 years ago, Seaford was protected by a stable shingle beach, similar to that now existing at tide mills immediately to the west. Late last century, however, new structures such as the New Haven Harbour Arm interrupted the natural alongshore eastward drift of shingle along the Sussex coast, causing the beach levels at Seaford to decline. To prevent flooding from the sea, a seawall was built. Unfortunately, the inadequate design of this wall caused the beach levels to decline even more rapidly. Waves breaking against the wall and reflecting from it over the years have scooped out the shingle beach and worn away the underlying chalk. During storms, the tremendous forces released by waves breaking on the wall abrade a way that forms the wall's structure. The thick steel piles used to protect the toe of the wall are bent and distorted. Beach levels are now so low that waves 6 meters high can arrive at the seawall before breaking. The existing wall was never intended to resist the forces from these large waves. In November 1985, the sea broke through the piling, and a hole the size of 3 double-decker buses was discovered underneath the wall at this point. Fortunately, the sea remained calm during the week after the breakthrough, and the hole was quickly repaired by pumping in over 500 tons of concrete. On taking over responsibility for the defences at Seaford, Southern Water carried out a comprehensive study of the problem and used hydraulics research to model various alternative schemes to solve it. From these studies, the most suitable and economic solution, estimated to cost £12.5 million, was determined. This would comprise a restored beach requiring the importation of 3 million tons of shingle, a terminal groin to prevent the loss of this shingle to the east, rock protection to support the most exposed length of the existing wall, and a future yearly recycling program to maintain the beach. Harbour and General were awarded the first contract in June 1986. This was for the construction of the terminal groin at Splash Point. The new groin was constructed from sheet piling and concrete and incorporates an existing sewer full within it. 16-metre-long steel piles were placed on either side of the existing outfloor. Each pile was interlocked with the previous one, carefully positioned and held vertical in a temporary frame. The piles then had to be driven into the firm chalk underlying the beach. A newly developed hydraulic hammer was used for the driving. This hammer was many times quieter than a conventional diesel hammer, and throughout the summer gave little or no annoyance to the nearby residents of Seaford. When a 9-metre-long wall of piling was complete on each side, all the shingle and soft material inside the piling was removed to form a firm chalk foundation for the concrete. At the landward end of the groin, this could be carried out by a hydraulic excavator working at low tide. When the excavation was complete, a closed box was formed by placing more piling at the seaward end. The box was then filled with concrete. The first stage of concreting was carried out by pumping. The lorry-mounted concrete pump was able to drive down and stand on the previously concreted parts of the groin. In this stage, The concrete had to be placed underwater up to 6 meters deep by means of the delivery hose from the pump. The concrete was delivered by trucks from a nearby batching plant in New Haven. As the concrete was placed and built upwards from the chalk bottom inside the piling box, it displaced the water above, which drained out to sea through the piling. During the whole operation, the delivery pipe had to be kept submerged in the concrete. Otherwise, cement would have been lost with the displaced water, weakening the concrete. Above the waterline, the concrete was tipped directly from the mixer trucks. Over 1,000 tons of concrete were sometimes placed in one day. Ground granulated blast furnace slag was used as a partial cement replacement to reduce cracking in the large mass of unreinforced concrete. Vibrators were used to move and compact the concrete, which was poured to just below the final finished surface and roughly leveled. The cycle for pile driving, excavation, and concreting for the next 9-meter box could then start again. On completion of all the boxes that formed the new groin profile, a continuous mat of reinforcement was laid on top of the groin. A thick slab of concrete was poured to form a durable finished surface to resist the action of the sea. The groin was completed at a cost within the tender price of £620,000 in 20 weeks. This was 2 weeks ahead of programme and in good time before the winter storms and resultant rough seas. The next phase of the works dealt with the stabilization of the existing seawall. Much of this length of the wall, despite having been reinforced or completely rebuilt up to 4 times in the last 50 years, was now at the end of its life. The most cost-effective way of stabilizing the wall was to place a protective layer of large rock immediately in front of the wall. The contract for this rock protection was awarded to Peter Burse for £1.4 million in September 1986. This contractor chose to supply the rock from a quarry on the coast of northwest Spain. Many factors such as the availability and the cheapness of the scene versus road transport contributed to making this a cheaper option than bringing in rock from the nearest suitable source in the UK. Blasting at the quarry took place every week. Approximately 10,000 tons of granite rock was brought down in each blast. The contract specified that the rocks required for the seafront should weigh between 7 and 15 tons. These had to be sorted from the blast, with the remaining rock going to a crusher for the production of aggregate, the normal business of the quarry. Any fears about the suitability of this hard granite were quickly dispelled. This piece of rock was dropped from a height of over 30 meters and suffered no more damage than a few chipped corners. A hole was then drilled in each piece of rock. An epoxy resin grout was mixed and poured into the hole. Threaded steel bar with a detachable hook eye was inserted into the hole. Within a few hours, the rock weighing up to 15 tons could be lifted, relying solely on the bond between the epoxy resin and the granite. Before reaching its final destination on the beach at Seaford, each rock would have to be lifted and set down up to 8 times. This simple and ingenious method of lifting was undoubtedly one of the main reasons for this contractor winning the contract. The rocks could now begin their journey to Seaford. They were first transported by lorry to the port of El Ferrol, some 7 kilometers distant from the quarry. They were then offloaded and stored on the quayside, until sufficient quantity was available to charter a ship to take them to New Haven. Up to 5,000 tons of rock were taken at one time, each rock being carefully stowed so as not to damage the lifting eyes. At New Haven, the recently installed container berth crane was used to transfer the rocks to lorries for the last leg of their journey to Seaford. Before placing the rock on the beach, a layer of smaller stones up to a meter thick was placed both to protect the shore seabed and form a firm foundation for the larger rocks. Two 100-ton capacity cranes were used to lift the rocks into position. These cranes had to stand on top of the seawall to place the rock. Great care was taken to investigate the ground conditions behind the wall to ensure that the load from the cranes did not precipitate the collapse. This contract was intended to avoid this. The contractor carried out all the placing during the winter when sea conditions often made work impossible. Nevertheless, with the quick and easy method of lifting, he was able to make full use of fair weather and would place up to 1,000 tons of rock in one day. All 58,000 tons of rock required under the contract were placed in 4 months, and the job was completed in January 1987, some 6 weeks ahead of the original program. All was now ready for the final and largest contract in the scheme to commence.
This was to comprise the importation of 3 million tons of sea-dredged shingle to replenish the beach. This contract was awarded to Zanon Dredging in January 1987 for the sum of $6.2 million. The method chosen by this contractor for placing the shingle was to pump it ashore directly from the dredger via a steel pipeline lying on the seabed. The 800mm diameter pipeline, nearly a kilometer in length, had first to be fabricated. This was carried out on the bank of the River Ouse, just to the north of New Haven. Pipes were delivered to the temporary fabrication yard in 20-meter lengths that were then welded together. Several pipe-laying bulldozers, a crane, and a tug lifted and launched the pipeline into the River Ouse. The pontoons shown here were to be used for beaching the shore end of the pipeline when it was in place at Seaford. The seaward end of the pipeline was to terminate at a large swivel pontoon. This pontoon was fabricated in Rotterdam and towed across the channel to the North Quay at New Haven. The completed steel pipeline was then floated down the river to be joined with this pontoon. The maneuvering and alignment of the long pipeline in the river to enable this connection was certainly one of the more difficult operations in the assembly. After waiting over 2 weeks for suitable calm weather, on the 14th of April, the long pipeline and all its associated pontoons were towed down the River Ouse, through New Haven Harbour and out into Seaford Bay. The shore end of the pipeline was beached while the swivel pontoon at the seaward end was manoeuvred over a prepared position on the seabed. Up to this time, the pipeline had been kept afloat by pumping compressed air into it. Once in position, the air was slowly let out, and the pipeline and pontoons were sunk onto the seabed. The pipe arm coming up from the swivel pontoon was designed so it could rotate through 360 degrees. To complete the delivery pipeline, a flexible floating rubber pipe was connected to the arm from the swivel pontoon. On April the 15th, the ship Barrett Zernan arrived to commence delivering shingle. Working on a 12-hour cycle, the ship steamed empty to the Ouse bank some 35 kilometers away, dredged and loaded the shingle, returned to arrive at Seaford just before each high tide, and connected up to the flexible rubber pipe. The ship's powerful pumps then emptied the 10,000-ton load of shingle in 4 to 5 hours, and the cycle started again. The shingle had to be mixed with large quantities of water and pumped at high velocity to avoid blocking the pipeline. When the ship was pumping, shingle was delivered at a rate approaching 1 ton every second. Nowhere before in the world has shingle been pumped such a long distance. Despite having to overcome many unforeseen engineering problems, progress was rapid and a 100-meter length of new beach was created every week. After 6 months, all 2.5 kilometers of the beach had been placed. Southern Water's scheme to protect Seaford was completed 1 year ahead of schedule, at a final cost of £9 million. £5 million of this sum was provided as a special grant by the Ministry of Agriculture, Fisheries and Food, with the remainder coming from county rates. On October 16, 1987, just as the scheme was finishing, the worst storm in 200 years hit southern England.
I lived in Seaford since I came here at the age of 3 in the 1950s, and I do remember watching the storms break over the seafront at the Salt Recreation Ground as I lived in a flat on Claremont Road and I could see them from the window. Seaford certainly dates back to Roman times because then it was a natural harbour. Small boats would have come in, trade would have occurred, fishing would have taken place. We would have been protected by the sea from the shingle spit that would have extended from Newhaven across to Seaford Head. Seaford lost its natural harbour when the shingle spit was broken through at Meaching and allowed the River Ouse to drain into the sea at what we now know as Newhaven. Well, the major development was really the development of Newhaven as a port. Coming in the railways, they decided they wanted to run ferry services, which required the River Ouse to be kept clear of silting up, etc. So they built a mole, which we now call the West Pier. Well, the building of the mole resulted in the loss of shingle hitting Seaford Beach by longshore drift. The shingle became depleted by that and for other reasons, and the risk of inundation by the sea during big storms increased. Well, the wall was the first hard engineering solution to the problems of Seaford and protected the low-lying lands of the former port. Unfortunately, the various attempts at building a seawall turned out to be inadequate, and on a number of occasions the seawall was breached, parts of the town were flooded, and everybody got rather annoyed. Although the seawall was built, along with the groins, we still continued to lose shingle from the beach. The answer would be a beach replenishment scheme. The scheme required the building of a terminal groin at Splash Point, this required the importation of tons of shingle dredged from out at sea and depositing it onto Seaford Beach. However, the action of the tides, particularly when it's a storm tide, will continually move shingle both east and west away from the central section.
Seaford is a picturesque coastal town nestled along the English Channel. But behind its serene facade lies a battle against nature's forces. Today, Seaford's seafront shingle replenishment is a carefully managed operation, orchestrated by dedicated contractors. Their mission: to move vast quantities of shingle from the east wing of the beach to the west wing, fortifying the shoreline against the relentless assault of the ocean waves.
We're responsible for the coastal and fluvial main river flooding in the county, so we manage all the flood risk assets that help protect homes and properties throughout the county. The shingle protects the seawall, which in turn protects the homes and businesses behind it. We do this twice a year. We tend to do it in the autumn after the half-term break, and then again in February after the half-term break. Here we have the harbour arm and the splash point groin, which helps us contain the shingle. So as long as we move quickly enough with the current operations, then we can not lose any shingle to the northeast or to the southeast around the coast.
Experts are working tirelessly to develop innovative solutions to mitigate the effects of climate change and protect vulnerable coastal communities like Seaford.
About 60,000 cubic metres of shingle, which is about 25 Olympic swimming pools worth of shingle we move in each phase.
The beach becomes a hive of activity as 630-ton trucks transport shingle to and fro along Seaford Beach.
Figures are consistent between 1.7 and 1.8 million cubic metres of shingle on the beach.
A total of over 25,000 tons of shingle is strategically relocated annually, replenishing the most vulnerable areas from Splash Point to tide mills in the west. But why the need for such a Herculean effort? The answer lies in the formidable strength of the waves that batter Seaford's shores. Positioned in the direct path of the South American Atlantic, Seaford is no stranger to the wrath of hurricanes. In the past, these ferocious storms have wreaked havoc, destroying the promenade and causing significant damage to the town itself. It became clear that a proactive approach was needed to shield Seaford from the destructive forces of nature.
Okay, well, the two big factors we consider when we do these operations are the October holidays and the February holidays. The angle that the waves hit the beach is not at right angles to the beach, so it pushes the shingle towards tide mills and towards Splash Point as well. Yes, we do. That's a big consideration of what we do, and we have some wooden markers in the ground where all the plant moves on the seaward side of those wooden markers, so that the vegetation is protected on the landward side of those wooden markers. Climate change is very real, and you know, we're seeing a pattern of extreme weather, and an increase in flooding and coastal erosion. So yeah, that's a big consideration in the work we do. We spend approximately between £800,000 and £1 million per year moving shingle up and down the beach, and this is still the most cost-effective method. To date, moving of the shingle is the most economically viable solution out there. Any other solution requires a big initial capital investment, as well as the unknown effects of the surrounding coastline.
Martello Tower sits right on the beach. Is it affected by your works at all?
No, it's not, and the heritage of Seaford is very important to us, so we make sure that our heavy plant moves a safe distance from all of the buildings and structures across the beach.
We realised that merely reacting to storm damage was not a sustainable solution. We needed a proactive strategy to protect our community and safeguard our coastline for future generations. Rising sea levels exacerbate the threat posed by storms, intensifying their impact on the town and its inhabitants. It's a stark reminder of the urgent need for a long-term strategy to combat climate change and its repercussions.
This shingle is continually moving and helping to protect Seaford from some of the most powerful waves in Sussex. Primary role is to reduce flood risk and protect people from flooding as best we can. And here in Seaford, we get to do that in the public eye, and we get such a positive feedback from the community for the work that we do.
But with determination, innovation, and collective action, Seaford will weather the storm and emerge stronger than ever.
Let your heart explore. Listen to the rhythm of the shore. Life is too short. It's just gotta be more. Mm.